In 1942, at the height of the Second World War, engineers were constructing a 26,500-ton giant, a bridge so critical that nearby Japanese bombing raids became an unintended test of its resilience. More than 80 years later, that engineering masterpiece, the Howrah Bridge, still stands. Remarkably, it was built without a single pier in the river or a single nut or bolt. Crossing the Hooghly River in eastern India, it links the neighboring cities of Howrah and Kolkata. The entire bridge is supported by just two main towers, positioned 1,500 feet apart. It is a suspension-type balanced cantilever bridge. Although the central span appears to hang unsupported, its load travels upwards through the steel structure and towards the anchor arms behind the towers. The sections extending from the towers over the river are called the cantilever arms. A conventional design would have just used two piers in the middle of the water. But here was the first major catch. Doing that would block massive ships and paralyze river traffic. The navigation channel had to stay completely clear, so engineers moved the supports onto the riverbanks, creating a brilliant self-balancing system. Moving these supports behind the towers and onto the riverbanks creates a balanced system. Each tower connects to a landward anchor arm, so the two arms act like opposite sides of a lever. When vehicles load the cantilever arm, the tower is forced downward while the anchor foundation resists an upward pull. However, both arms are too long for unsupported steel to carry heavy loads at their outer ends. They therefore require support from above rather than below. The aim is to collect loads acting anywhere along either arm and transfer them safely to the main tower foundations. Each main tower consists of two separate posts rising 269 feet. Case-shaped bracing connects them, dividing the large vertical frame into smaller, more stable panels. This reduces the post's effective slenderness and distributes loads between them. An upper cord then extends from the top of the tower towards the cantilever arm. Forces from the outer end of the cantilever arm travel through the upper cord to the tower. Although the anchor arm balances the overall load, the cord still pulls the top of the tower toward the river. Now, picture this. Under extreme traffic loads, this entire steel region is under so much tension it could bend, snap, or completely fail. To resist this pull, another cord extends from the tower top towards the anchor arm. The cantilever is now supported from above and balanced by the anchor arm. But this connection alone is still insufficient. The cantilever arm extends 468 feet, while the anchor arm extends 325 feet. As loading near the center increases, the steel bends progressively. Excessive bending could cause either arm to fail. A single connection near the end cannot support the entire cantilever. The upper and lower cords are therefore linked at several points by strong vertical steel members. The anchor arm uses the same arrangement. The upper cord does not pull the cantilever straight upwards. It transfers force diagonally towards the tower. This places lateral forces on the long vertical members, which could bend together under heavy loads. K-pattern diagonal members therefore brace the verticals and shorten their unsupported length. The anchor arm uses the same truss arrangement. This system transfers loads from anywhere on the bridge through the truss to the towers, primarily as vertical forces. Each cantilever arm was erected as a continuous structure extending from its tower. A creeper crane traveled along the completed steelwork, lifting and connecting new members before advancing with the growing cantilever. This eliminated the need for temporary supports in the river. Transverse members connected the two parallel cantilever trusses, tying them into a single rigid structure. The anchor arm foundation is unusual because it must resist uplift, not just downward compression, despite being constructed from concrete. A steel member can carry tension when lifted, whereas a concrete block may crack through the middle. The anchor foundation faces the same risk under uplift. Each anchor arm foundation was built separately, rather than excavating an open pit in unstable ground. Engineers constructed large reinforced concrete caissons above the site. Steel cutting edges around their bases helped the caissons penetrate the soil as they descended. Internal walls divided each caisson into two working shafts. As soil was removed from the shafts, each heavy caisson sank under its own weight. At the required depth, the shaft bases were sealed with concrete plugs to stop river water entering from below. Anchor links were installed from the base of each foundation before the remaining space was filled. A large concrete structure then joined the two foundation units into a single solid mass. Finally, the upper ends of the links were connected to the anchor arm steelwork. Under bridge loading, the anchor links tried to lift the entire foundation. If repeated vibration loosened them within the concrete, or if the foundation offered insufficient resistance, the bridge could tilt towards the river and collapse. Heavy anchor girders were embedded within the foundation to distribute this uplift. Connecting the anchor links to these girders spread the force across the entire concrete mass. Adjustable packing on both sides of each anchor girder allowed minor movement and alignment at the connection, preventing concentrated forces from damaging the concrete foundation. Constructing the main tower foundations was even more challenging. Open excavation was impossible because water and soft riverbed soil would continuously enter the pit and destabilize its sides. Engineers therefore built the enormous reinforced concrete caissons, each measuring 181 by 81 feet. Steel cutting edges around the base helped them sink through the soil. Dredging equipment removed soil from inside each caisson, allowing the massive structure to sink gradually under its own weight. Here's where things got extremely dangerous. The entire foundation was at risk of a catastrophic collapse. Wet soil and groundwater exerted constant lateral pressure on the caisson walls. This pressure increased as the caisson descended, acting across its large outer surface. Without internal support, the walls could bend inwards, buckle, and eventually collapse. Internal stiffening walls prevented this by dividing the caisson into 21 smaller shafts. Soil could be dredged independently from each shaft, giving engineers precise control over the descent. If the caisson began to tilt, removing additional soil from the opposite shaft helped restore its alignment. Under normal conditions, the caisson descended by about 1 foot per day. Then at 2 a.m., the unthinkable happened. The massive caisson suddenly dropped 2 feet without warning, shaking the ground like a powerful earthquake and collapsing a nearby temple. On the Kolkata side, the caisson reached firm rock at 103 feet. On the Howrah side, it reached rock at 87 feet. This stratum could safely support the bridge's immense weight. Even after reaching firm ground, water could still seep into the shafts from below. It was pumped out before each base was sealed against further seepage. Some shafts were backfilled to the height of 5 meters, with concrete placed above the filling. To balance the caisson, their upper sections were deliberately left hollow. Completely filling every shaft would have added excessive dead weight, potentially driving the cutting edges deeper and causing further settlement. A thick, heavily reinforced slab tied all 21 shafts together, allowing the foundation to resist loads as a single solid mass rather than as separate chambers. This unified structure is known as a monolithic foundation. Above these foundations sits a gigantic skeleton of high-grade steel. To put this into perspective, engineers used roughly 26,500 tons of steel. That's equivalent to almost 3 Eiffel Towers. Over 23,000 tons were manufactured locally by Tata Steel in Jamshedpur, while the rest was shipped directly from England. Once the cantilever arms were complete on both riverbanks, a 564-foot gap remained for the central suspended span. The suspended span was erected simultaneously from both sides of the river. Pin joints at the ends of the cantilever arms allowed the connected sections to rotate slightly rather than remain completely rigid. Articulation joints also accommodated movement caused by changing loads and thermal expansion. The bridge contains 8 such joints, 1 at each end of the suspended span and 3 along each cantilever arm. This controlled flexibility allows individual sections to move without generating damaging internal stresses. Temporary ties were installed along the top of the suspended span during erection. As its 2 halves extended toward the center, their own weight caused the free ends to deflect vertically. Eight hydraulic jacks on each side were then used to lift and align the steelwork. These tiles allowed the required movement while preventing the incomplete span from becoming unstable during adjustment. Once the 2 halves were perfectly aligned, large gusset plates connected the steel members across their meeting points. Every hole had to align precisely before the final connections were made. Remarkably, the bridge used no nuts or bolts. Its structural members were joined entirely with rivets. Each rivet was heated, inserted through a drilled hole, and hammered to form a second head. As it cooled and contracted, it permanently locked the joint. Why were rivets chosen instead of nuts and bolts? Consider the reason and share your answer in the comments. The steel skeleton was complete, but the road deck still had to be suspended beneath it. 39 pairs of hangers carried the deck load from the cross-girders into the main trusses. Longitudinal steel members were laid over the cross-girders, followed by floor beams to support the roadway. Fascia girders were installed on both sides of the bridge to support the footpaths. Reinforcement was then installed, and the concrete road slab was cast. Hangers were unnecessary above the anchor arms, where the deck could rest on the ground-supported approach structure. Each footpath is 15 feet wide, while the main deck slab is 71 feet wide. Today, hundreds of thousands of vehicles cross the bridge, which remains operational more than 8 decades after its completion. This explains the main engineering challenges involved in constructing the Howrah Bridge. For more engineering stories, subscribe to the channel. Thank you for watching.